Okay, so spectroscopy part 2. So the dynamic duo. I like that one. Okay, coherent radiation, Eustacio. The picture's supposed to kind of tell you. It looks like with coherent radiation,
It's supposed to be parallel.
kind of parallel, but all the what are lined up?
The waves.
Yeah, the waves, like all the peaks and valleys. The word would be in phase, right? All the peaks and valleys are in sync. So that's what coherent radiation is.
So coherent means in wave.
Well, no.
In sync.
See, look at the diagram.
Phase.
Yeah, in phase, or all the peaks, all the troughs, all the valleys are lined up, right? They're all in sync. Diffraction. Diffraction. What is diffraction? So Bradley, we've got a little animation here. Is this diffraction?
No.
No. What is this?
I thought diffraction is when you split waves.
All right. Water dripping.
That's diffraction.
No, he's right. This is not diffraction. You thought diffraction is when you what?
I thought it was like the splitting of the waves.
Yeah. The waves have to be bending around a corner or an edge, right? So if I get rid of that slit, this is just interference, right? You get constructive and destructive interference. You're talking about water, it'd be big waves and little waves, right? With light, bright spots and dark spots on, right? So you have a dark spot, bright spot, okay? Is this diffraction? No. This is pretty much interference or something, right? Just waves in a box. Nothing's really happening here. But if you have some peaks and valleys forming, but it's coherent. This is coherent radiation. So if you add a barrier, right, something for it to travel through, this is diffraction. Because now you get some bright spots or something, but it's bending around an edge. Okay, that's diffraction.
So that would make a wave.
Yeah, interference is also a wave property too. Okay. Oh, I see what you're saying. So diffraction is a wave property, right? What does a circular diffraction pattern look like? Okay, so let's see if we can show you. You got to come up and look at this. You got to come up and look at this. Okay, so what I'm going to do, here's a laser, right? I don't know if you can see it. I don't know, I was thinking of standing up here. Maybe you can see it from there, but you're definitely going to have to be, I would come up here, because you're going to have to see this thing. What I'm going to do is I'm going to find a little dot here. There's a little pinprick on this. So I'm going to shine this light through the pinprick. And then, but it's not like in that diagram, like in that animation, it was just a box. Now it's going through a circle. So what is the diffraction pattern going to look like? So that's what I want you to see.
So we have to come out there.
Yeah. Once I find that little pinprick here, where is it? God, it's so damn bright. There it is. All right. Then take a close look at it. Oh, I lost it. You see it? You gotta look really close up at it. What does it look like? Maybe my hole's too big. It should look like a target. I don't want to tell you, but it should look like a target. Let me make another pinprick here. It should look like a target. That's right there. Damn, it's so hard to see without the lights on. All right. Yeah, the hole was too big before. See, so you see the fringe, you see the bright and then the dark and the bright and the dark, those fringes that go around in circles?
So that type of diffraction just kind of looks like
That
That's not diffraction.
That's a circular diffraction pattern.
That is.
So I want you to sketch that. Sketch that in that space that you got there. That's what a circular diffraction pattern looks like.
But that kind of looks like a drop of water.
So that's different than the interference.
Well, you need interference to get this. But the point is it's all interference. But diffraction is a special case where there's actually passing through a barrier. And then you have something's going on. You can pass through all these different barriers. You pass through slits. You can have double slits. You can have single slits. You can have circles. So what you are drawing is what a circular diffraction pattern looks like.
Do we draw these little things that were kind of like coming off the edge of the circle?
No, I guess I'm more after, a really bright spot. Well, since it was red, I should be drawing it in red, right? So really bright in the center. And then it was dark. Then didn't you have a bright ring, dark, bright ring, dark, something like that, right? Should have seen something like that. Hey, and you're right, it's more complicated. There's a little thing sticking out because I didn't get a perfect circle on here. But that's the idea. So the addition of waves is pretty complex. We have two tuning forks, and they're differing by a few hertz. For example, this one says 320 hertz, and this one says 320 hertz, but look how banged up they are. So they're differing by a few hertz. Okay. So what do you hear when they're struck together? So if you hear just one, right, just a regular tuning fork sound, right? What's still there? Right? It's still there? So regular tuning fork sound. Now if you hear them together though, now what I want you to hear is a wah, 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 wah. You hear a beat.
Now I got it. Wow. That probably my.
There's a wah, 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 wah.
And that's because they're off.
What's still there? See, it's a wah, 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 wah. So just by, this is like 320, this one, but it was like wah, 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 wah. So how many is that per second? Like 3 maybe or something? So the difference is 3 hertz. And that's just 2. That's just 2 frequencies. But imagine, remember, we're talking about light. Yeah, this is sound, but waves are waves. So look at the FTIR. You've got literally thousands of frequencies going on at the same time. Not just 2. 2 already cause you weird things like beats. But you have thousands of frequencies going on. So it's getting really complex, this addition of waves. So let's see here. Reflection, refraction, diffraction. Man, you got a bunch of these. What's the difference between refraction and reflection? Well, let's just use pictures to tell us, right? Like this first one. Kevin, you put a straw, all right? Can you see how there's a break there? You've seen that before. What is that? Which one is that out of these 3? That's refraction. Good. How about B? Now, what's going on in B, Shelby? They're shining white light into a glass prism, right? And then you get Roy G. Biv out, and that is so different wavelengths. They say, well, this is the argument kind of, travel different speeds in the same medium, so in the glass. They're saying that they're going to bend more or less. It's kind of like the straw idea. except now we're talking about individual wavelengths of light. So they're going to bend differently. If that straw had different colors, that would, I don't know if you could actually tell. That'd be interesting, right? Different colors of that straw. You'd actually see different refraction, it was shifted more. It's not shifted as much for shorter wavelengths. I kind of think of it as if you're a short wavelength, right, you're getting out of that, you're really compact. You're getting out of that prism faster. I don't know if that helps or not, because all light travels at the same speed. But anyway, different wavelengths are going to bend differently. That's the whole idea of refraction. So it's refraction. It's kind of it's the same as the glass idea, but it's just you're different medium. It's not water anymore. It's a prism, and you're getting all these different colors of light. You're not talking about a straw anymore, but you're still talking about light, because that's no other way could you see the straw. How about C? Yeah, there's a diffraction. That's a single slit. And it's going to create some pattern over here, right? Some intensity pattern. I think we saw that, didn't we? Yeah, here's the intensity pattern. You get a bright spot in the middle, right? How about if you did 2 slits? What happens? You should get, it's going to get kind of complicated. Looks like you get a little, see, isn't that weird? This is what I like about diffraction, is it really creates the wave and not particle property. Because there's no way a particle is going to hit right behind this thing. There's no way that particle is going to hit there. But diffraction allows it to get there. And when you start taking chem and more advanced classes, the only way to explain a lot of things is to call particles and objects waves, which is ridiculous. Because if I'm a wave, that means that not only am I here, I'm also over there, over here. So it gets to be a very weird world.
Systemic normalization. Your probability density of being there versus everywhere else.
All possibilities must be there at once, otherwise you're not going to get the right answer. It's weird, very weird. Okay, how about
Diffraction.
yeah, diffraction again. Now it's going around something solid. Okay, you get some weird patterns there. How about E?
Reflection.
That would be diffraction.
So
Seeing the light
you're gonna
back at
you're the dude and you have a gun or a bow and arrow. You're gonna shoot those fish, right?
Wait, what?
You see what I'm saying? That's what they're trying to illustrate here.
You're shooting fish again?
Well, he could be. If he doesn't take into account what, he's gonna miss.
Diffraction. Or refraction.
We called it refraction, right? If you're looking in the water and things shift on you, it's refraction. So you got to take that into account. Plus, wear your Babe Winkleman sunglasses, otherwise you won't see them in the first place.
So that's not representing the light coming back at him. His eye?
Well, they're trying to represent the real position, and then the position that he sees. So here's like the real position, and then they're trying to say, oh, this is what he sees. So that's refraction. F would be refraction, because now it's different. It's different than B. Now it's passing through not a prism, but
Through a slit or whatever, so it's diffraction. So
through a
Polarizing lens.
what do we call these? Grating, but we always call them a what grating? Diffraction grating,
oh, okay.
right? So it's diffraction.
Things are making sense.
So it's diffraction, diffraction grating. So it's the same idea
So that's like
as this one,
going through a hole or something,
right?
around something.
But it's not being refracted now. It's diffracted. There's actual lines and stuff on here that on the order of the width of that, on the order of the wavelength of the light, it's diffracting. So diffraction, refraction.
Is that all
What
G?
is this? I think G is,
Reflection.
it's supposed to be more gratings. I just got some pictures of some diffraction gratings, but they have a mirror on the back.
So this is diffraction.
So that's diffraction again. So it's diffracting. It's probably what you'd see in a lot of like monochrometers, which haven't talked about yet.
Feel confident that H is
In fact, this would be yes, this would be a nice picture to add when we add monochrometers. Because if I can remember that, because this is a key piece that makes a monochrometer work. What's a monochrometer work? You have this nice big light bulb, but you only want 520 nanometer light. You only want red light. Well, big black box in front, your monochrometer. And the key piece in that big black box is that grading element. Okay. Last one, this would be
Reflection.
yeah, reflection.
It is refraction.
The Fourier Transform. Okay. We haven't talked about FTIR, the Fourier Transform infrared spectrophotometer, but it uses a Fourier Transform, right? FTIR. Let's go put our sample on the FTIR, right? The FT is the part we're talking about. So, God, I might as well just tell you a little bit. There's a, oh man, a Michelson interferometer. I don't know. I mean, I shouldn't be saying all this. This is going to really confuse you because we haven't talked about FTIR yet. But the reason why I mention it is because what class is going to be building a Michelson interferometer in lab? You better say it. PChem. It's a PChem lab.
physical chemistry.
We build a Michelson interferometer. So this, I think I shouldn't. Let's just leave it at this. You have something moving inside that Michelson interferometer, and it's an actual mirror that's moving in distance, and it's getting some signal out of it. Well, you need to transfer that information of this distance that it's getting into, oh, the carbonyl stretch at this wave number, right? Or the OH stretch, right? You need to go from this one domain to another domain. And very often that's just use the Fourier transform for that, or sometimes the inverse Fourier transform. But the point is you can go from one domain to another. Let me give you an example of this. Well, let's just read this over first here. The Fourier transform can be used to determine the different frequencies in a signal, right? It's kind of like in that FTIR. You have all these frequencies going on at once. Which ones are attenuated a little bit because the carbonyl stretch changed, for example. For example, in an absorption signal, it can determine all the frequencies that were absorbed, all at once, all at the same time. In a song, you can tell all the frequencies that are present. Okay, so, okay, let's see. So in this animation, starting with one frequency, add additional frequencies. How does the Fourier transform signal change? I guess I remember what the heck I'm doing. Okay, let's close that one. Let's go back and try this one now. So these I've just added. I'm still playing around with them. Drag me. Okay. So what I'm going to do, oh, we need sound. We need sound. So what I'm going to do is start with a frequency that we can hear. Still can't hear it. Can't hear anything. Why can't we hear anything?
Volume's at half.
Where's volume?
Sound control's volume.
Oh, I didn't turn the sound on. All right, so that's one frequency. Right? But life is a lot more complicated than one signal, right? So look what happens. Okay, now, well, let's turn it down so it's not so nauseating. So as I add a lot more frequencies, look what's happening to, this is the frequency domain. Now there's this domain where they're actually talking about space, distance. And as I add more and more, how can I make this guy? Oh, there it is. Now you can see it better.
So is that supposed to be...
Let's go back so you can see how it grows here.
So is the sum just the, I guess, the average of all the waves together?
Yeah, all these waves added up. Okay, let's go back to 1. All right, so here's the frequency domain, okay, how things are changing in the x direction. You add more and more waves. Look what's happening down here. It's getting more localized. As you add more and more frequencies, you really don't have much idea what the frequency is, but in the Fourier transform, the distance domain, it's getting much more narrowed down. So if you want to narrow something down, even make it really, really sharp and know exactly the signal at the, what the x distance is, for example, you need a lot of frequencies. If you want to look at it the other way, if you want to nail the frequency down, just have that one frequency. Look at the x. Where the hell is it? This is the Heisenberg uncertainty principle in pChem. It's just, you can't have one without the other. You can't know where something is and know the frequency at the same time. 2. So it's kind of, this is what I think another lab in pChem that they're playing around with. Not this thing, but something else. Okay. But that's, so in the animation, starting with one frequency, then adding additional frequencies, how does the Fourier transform signal change? It gets more bunched up, like a center burst, right? On the FID, you see this center burst, right? The more frequencies that you measure, it's just a different domain. So how can you think of this center burst? You can think of it as a distance where this little mirror's moving, the light's really bright, or you can think of it as a little microphone that once you're at that spot, you hear a big, bright sound and you don't hear it anywhere else. But you need a lot of frequencies to generate something like that. And what are those frequencies? Do a Fourier transform to get exactly what all those frequencies are and their amplitudes. So yeah, these are just like sound analyzers, which is what they play with in pChem again. So we're talking about spectroscopy, light interacting with matter. There's 2 types of scattering. One is Rayleigh, and it occurs when the scatterer is smaller than the wavelength of light being observed. Whoop. So you have to have a scatterer. Something has to, that the light has to strike and has to be incident upon to scatter it. So if the scatterer is smaller than the wavelength, then it's called Rayleigh scattering. And there's no change in frequency. So in other words, and it's hard to get used to this, usually when I think of different colors, I think of different wavelengths. Well, those are also different frequencies. Those are also different energies. You can use the same word for all that stuff. So different colors, right? No change in color would happen during the scattering process. No change in energy, no change in wavelength, no change, right? All those would be the exact same thing if it's Rayleigh scattering. And the shorter the wavelength, the easier it is to scatter. Okay, so if, what it would, now we can only see Roy G. Biv. What color in Roy G. Biv would be the, well, let's ask this question first. I think it was on the quiz. What color is the most difficult to scatter? All right, let's just follow this. What is the best color to use to view through fog?
Reds and yellows.
So you want something that you want, because that's a hint. You want something that's going to, right? I guess the hint is right here. The shorter the wavelength, the easier it is to scatter. So you want a color that can penetrate all this stuff and not be scattered.
So red is the shortest visible.
Well, red would be wouldn't red have the longest wavelength?
Red would have the longest wavelength. What has the shortest wavelength?
Violet.
Violet. So the shorter the wavelength, the easier it is to scatter. Now, scattering's a bad thing. You're a fog light. You want it to penetrate through. So violet would be horrible.
So we want red.
So you'd want red. But your eye isn't very sensitive at red. So they make the fog lights yellow. Plus, red also means rear lights, right? So that's probably would be a good thing to make as a fog light, okay? So But the question is, what is the best color to use to view through fog? I would say red might be. But your eye isn't very sensitive to red, so maybe an orange just kind of hue. Okay.
So is that why, like, night stuff when you're going out and you're doing astronomy or hunting or stuff like that, we always use red lights for everything?
No, that's so that your eyes can get used to the dark. Because your eyes, remember, you're dropping off. Roy G. Biv. After red, your eyes are already dropping off at red. You can't see red very well. Violet, you can't see violet very well. Right in the very middle is that stupid color that they put on those LEDs, on DVRs and everything. It's that lime green thing. Did you ever notice that? That little lime green LED lights up a whole room when you shut off the lights. Your eye is so sensitive to it. So I think they've gotten better with it, but some equipment still, some electronics still has it. So your eye is really sensitive to this, but it has a short wavelength, so it's going to scatter. So the whole idea with astronomy is, no, that's all, keep that pupil really big. That's using red light. This bugs the crud out of me. I get easily perturbed. I'm trying to change my outlook on life here, but I still get perturbed. You're driving down the road, right? You know what headlights I'm talking about?
Yeah.
They are so bright. Why are they so bright? The HIDs, why are they so bright?
Because they're pure white.
What color are they kicking out? In Roy G. Biv has all the colors, but in that, they're kicking out a lot of what color? White isn't in Roy G. Biv. They're kicking out a lot of blues. And what's the problem with blue? Blue is really, blue, violet, whatever, it's really short. So is it easy to scatter? Yes. All that blue light, you don't see, those HID lights don't bother you until you're right up on front of them. And it's just all over the place, right? It's just scattering everywhere. They're not penetrating. So they're horrible, right? And the dudes who's driving them, they think, oh, this is fantastic. They see every detail on the road in front of them because it's so bright. But go 10 yards, 20 yards down the road, he can't see jack. So it scatters it right in front of that car. The light can't penetrate. If it's being scattered, it can't penetrate. So if this is the vehicle, he's got those HID lights, it doesn't bother the person coming until right here, and oh my gosh, right? And that's dangerous. And this guy's happy the whole time because he can see everything right here. But he's not going to see the little dude crossing the street down here because he can only see everything in really nice detail right here, right? It's messed up, but that's what they do. Oh, I already answered this one. LED lights on electronics are very small. However, even so, there's one color in particular that can light up a dark room. Yeah, it's that lime green thing. Okay, your eye is so sensitive to it. Why is the sky blue?
Because nitrogen reflects blue, right? Because blue is a short wavelength.
Very good.
So easily seen.
Nitrogen is a blue scatterer.
That's E for below buff.
Nitrogen is a blue light scatterer. Perfect for that. So what type of scattering is that? If nitrogen scatters blue light really well and we see blue up there, would that be... That's Rayleigh type scattering, right? Because it comes in blue, reflects blue. So if you go to a planet that doesn't have nitrogen gas, or it doesn't have very much, doesn't have 71% nitrogen like we do, will its sky be blue? No. If you go to any planet that does have 71% or more, will its sky be blue?
71% or more, yes.
Yeah. Mm-hmm. Okay. During a sunset, it's red.
So nitrogen goes away.
Why is it red?
Is it something to do with like refraction?
All right.
It has something to do with the angle of the refraction of the light wave.
Okay. I'm not very good at drawing, but let's say
It's a big Earth to sun.
it's a bigger guy. All right. So this would be noon, right? Because it's a planet's gravity, so I don't have to be standing on top of it, right? So here's the sun, This is be noon, where you're looking up, right? How would you change it to evening? Where would the little dude be?
The dude would be either on the bottom or on the top. He's rotated, we'll say 90 plus 90 degrees.
He's got to be where the sun, you can't see the, he's got to be where he can just barely see the sun, right? His little head's going to be just barely over here, right? So he can just barely see it. Make sense? Okay, so there's the two cases. Let's put this guy back. Which one is the sunlight passing through more atmosphere?
Which one has a sunlight?
Which one is sunlight passing through more atmosphere? Is it the noon guy or the evening guy? It's evening.
Yeah,
Most definitely the evening guy. It's got to pass through a lot more atmosphere. That means a lot more scatters. What's the only wavelength that can, what's all of that stuff?
long wavelength,
Which would be red. So the sunlight, the sunset's going to go from, well, the sky is blue, so that kind of messes stuff up. But you'll go from your yellows to your oranges to your reds to your deep reds, and then it's gone.
Can you give us a moment
To reflect on the beauty of nature.
to, yeah. Like refraction and nitrogen.
Okay. There's nothing really to talk much about Raman, except Raman is actual spectroscopy now. Because in Raman, it's scattering, but the frequency has changed. So you can have things, if red light's coming in, it's not going to scatter red light anymore. Either it's going to get a deeper red, or it could go the other way and get bluer. So it could red shift or blue shift. So in Raman scattering, these collisions, these scattering processes are not elastic. They would be inelastic, would be the technical jargon for it. But the point is, energy is either lost or gained when you're scattering for Raman. So you're going to hear of the term Raman spectroscopy because there's actual interaction between light and matter. We don't have one of those, but okay. Photoelectric effect. Bradley can tell us what the photoelectric effect is, since we talked about this in P-Chem, right? So pretty much, I forget how to set this whole thing up. So you're shining, whoa, whoop, okay. You shine light on a hunk of metal, okay? And you can make it super, super bright. And the photoelectric effect is just, once you reach a threshold, you can finally eject an electron out. But the point is each little photon at 728 nanometers, it doesn't matter how many strike that metal, because the intensities don't add up. It's acting like a particle now. The whole wave idea is gone. You'd think with waves, things would add up, you can knock out a particle. Just make it a laser at 728. No, it doesn't work. It's acting like a particle now. So the particle comes in. If each individual photon particle doesn't have enough energy, it can't kick an electron out. So I can make this as intense as I want, right? It's not going to kick anything out. I have to, so I crank up the energy some more, right? So as I go down in wavelength, the energy is getting higher or lower. And make this down in wavelength, energy is getting higher. So I'm going to make this intensity really low. All right? I got to be kicking out something sooner or later here. There, the threshold must be around here. You see something came out of there? There it goes. So if I go just a little bit lower in energy, crank up the intensity, oh, I must have missed it. Where's that threshold? I must have missed it. Here it is. It's somewhere in here. Somewhere in here. The point is, as you crank up the intensity up here, nothing happens. but where it's coming out and make the intensity really low, you can get it. Whoa, it's a zero, ain't gonna work. You see what I'm trying to say? Once you reach a threshold, the intensity has nothing to do with the photoelectric effect. You just have to reach a threshold in energy for that photon. And either it's going to, if you reach that threshold, it'll kick out an electron. If you don't reach that threshold, intensity doesn't matter. So I could make the energy of a photon really strong, make the intensity really high. Yeah, I'm going to kick out a lot of electrons. But I can make the intensity really low and still kick out one electron. But you can't play that game if you're above the threshold. It doesn't matter what the intensity is. You can't kick anything out. Does that make sense? So just think of it as, instead of looking at wavelength, just call it an energy. 2 joules. You need 2 joules to kick it out of energy. To kick an electron out of this hunk of metal. And it travels over here because this is positively charged, so that's why the electron shoots over there. So if I don't have 2 joules of energy, it ain't going to kick anything out. I can crank up the intensity as much as I want. It doesn't help. I have to have 2 joules of energy or more. So down here, I definitely have 2 joules of energy. So it doesn't matter whether I have 1 photon or a bunch. I'll kick out an electron. Because each electron has 2 joules of energy or more. So that's the photoelectric effect. I don't know if that's very important here. It's just in the book, so that's why I presented it. So we have a table to fill out here. Atoms and molecules are always in quantized energy states. They can undergo transitions between these energy states by absorbing or emitting light. So we have different types of motion and their types of transitions. So you have electron motion about the atom or molecule, right? That's orbitals, right? And they call those electronic transitions. You have vibrational motion in the molecule. Well, they call those vibrational transitions. Molecules could rotate, right? Or molecules could spin. Their nuclei could spin. So these are just the types of motion that would, if you absorb this radiation or emit this radiation, this is the motion that changes. So you're just, right? That's interaction of light and matter. So what type of instrument does each one of these do? You've used these. Which one deals with, I'll just tell you since we're running out of time. The UV vis deals with electronic transitions. But you should know vibrational, well, we haven't talked about it yet, but maybe you might know. Vibrational motion in molecules is which instrument up there?
I'm sorry, what?
Which instrument messes with vibrational transitions? Vibrational motion in molecules. Yeah, carbonyl stretch. You have an OH stretch. Water does the scissoring. What is it? It's the infrared, the FTIR. You've got rotational motion of molecules. We don't have one of these. Microwave spectroscopy. And then you have rotational spin of nuclei. NMR. Okay, last thing, and then we can get out of here. So absorbance, this is absorbance. They should have, I don't like that they don't do this. You should have a little wavelength symbol on these. Because absorbance always occurs at 1 wavelength. So then you have this little molar extinction coefficient. It's just how good can your molecule absorb at that wavelength. So it's just a number. If it can absorb really well, it's going to be big. B is this, our path length, right? Because this is our cuvette. You slide into the UV vis. You need some kind of path length. That's B. And C is the, does anybody know? What else would increase absorbance? Concentration. Perfect. Concentrations. Okay. Always transmittance is P over P naught. So P naught is this incident intensity. And P is the transmitted intensity. So,
That's the cuvette, the sample.
yeah, so the cuvette or whatever it is holding your sample. So you've heard of transmittance before, and then you've gone from transmittance to absorbance, and the computer just did this. A is negative log of T. So you've got a couple of equations. We're not going to really use any of this stuff. It's just for you to know. And then Beer's law is this one on the bottom. So absorbance is really epsilon BC, molar extinction coefficient, path length times concentration. But you can also get absorbance by finding the negative log of transmittance. Or what's transmittance? You have to make two measurements. Transmitted intensity divided by incident intensity. And then you'll have it. So that's it. We went over by a couple minutes.